For decades, humanity has been captivated by a powerful dream, a vision repeated in documentaries, scientific conferences, and billion-dollar space programs. The dream says that Mars is waiting for us, a distant red frontier that will someday become humanity's second home. We imagine astronauts planting flags into crimson soil, building colonies beneath transparent domes, and eventually turning another planet into a backup civilization for Earth itself. But buried deep inside this inspiring narrative is a dangerous assumption that almost nobody stops to question. An assumption so fragile that the entire dream of returning safely from Mars may collapse under its weight. The assumption is simple. We believe a spacecraft launched from Earth can travel hundreds of millions of kilometers through space, land on Mars, sit abandoned on the surface for well over a year, and then suddenly ignite its engines perfectly on command to carry human beings back home. That confidence sounds reasonable when presented in clean animations and polished presentations. But once the laws of physics enter the conversation, the picture becomes far more disturbing, because the greatest threat to a Mars return mission is not launch failure. It is not radiation. It is not even the long journey itself. The real enemy is time. Every single day, a return vehicle sits motionless on the Martian surface. Invisible damage slowly accumulates inside it. Tiny failures begin to grow. Materials expand and contract. Protective systems weaken. Mechanical precision starts disappearing molecule by molecule. Entropy quietly takes control. And by the time astronauts attempt to leave Mars, the spacecraft they trust with their lives may no longer be the same machine that originally landed there. To understand this, imagine taking one of the most advanced engines ever built. Remove all protection around it and leave it exposed inside a freezing sandstorm for 2 full years. Temperatures violently swing from extreme cold at night to warmer conditions during the day over and over again without stopping. Dust constantly slams into every moving component, and no mechanic ever inspects it. No replacement parts arrive. No fresh lubrication is applied. After 24 months of nonstop abrasion and chemical corrosion, someone suddenly demands that engine perform at maximum power instantly because human lives depend on it. You already know what would happen. The seals would fail, valves would stick, internal surfaces would crack under stress. Instead of saving lives, the engine would most likely explode. That is not science fiction. That is the real operational reality of launching a spacecraft off Mars after leaving it unserviced on the surface for more than a year. And the deeper scientists examine the problem, the more unforgiving the physics becomes. In the next part, the brutal mathematics behind rockets themselves begins to reveal why Mars may be far more dangerous than most people realize. The deeper we look into the problem of returning from Mars, the more the universe begins to feel less like an open frontier and more like a system built to resist us at every step. Because once the romance of space exploration fades away, one brutal reality remains standing above everything else. Rockets obey physics, not ambition. And the equation controlling them may be one of the most unforgiving relationships ever discovered. More than a century ago, Russian scientist Konstantin Tsiolkovsky developed a formula that still governs every rocket humanity has ever launched. At first glance, the equation looks deceptively simple, but hidden inside it is a terrifying truth. Every extra kilogram added to a spacecraft creates a chain reaction of increasing fuel demands, and that chain grows so aggressively that eventually the numbers stop becoming practical at all. The equation explains that a rocket's speed depends on 2 things: the efficiency of its engines and the ratio between its starting mass and its final mass after fuel is burned away. That sounds manageable until you realize what it means in practice. To carry more equipment, you need more fuel. But adding more fuel also increases the vehicle's weight, which then requires even more fuel to lift the added fuel itself. The system begins feeding on its own mass. Now apply that reality to Mars. A spacecraft leaving the Martian surface must accelerate to roughly 3.4 kilometers per second just to enter stable orbit. It must achieve this while carrying astronauts, carrying life support systems, navigation equipment, shielding, and enough supplies to survive the long trip back to Earth. Even though Mars has weaker gravity than Earth, its atmosphere is so thin that it offers almost no aerodynamic assistance during ascent. The rocket has to fight nearly the entire battle using pure chemical thrust alone. And here is where the trap closes. The return vehicle cannot simply sit exposed on Mars for over a year without protection. Engineers know it needs insulation, reinforced seals, protective coverings, redundant systems, and shielding against dust and temperature extremes. But every layer of protection adds dry mass to the spacecraft. Every kilogram added for safety triggers an even larger increase in required propellant. And because the rocket equation punishes mass logarithmically, the problem does not grow steadily, it grows exponentially. Suddenly, the mission architecture begins collapsing under its own weight. To protect the spacecraft properly requires more fuel. More fuel requires a bigger rocket. A bigger rocket becomes heavier to launch from Earth. That heavier launch requires even more fuel and structural support. The cycle keeps expanding until the entire system approaches physical impossibility. This is not a failure of engineering creativity. It is the direct consequence of physical law. Rockets are not machines that can simply be improved forever through optimism or determination. They are trapped inside the mathematical boundaries imposed by momentum and energy conservation. So modern mission designs often fall back on a dangerous compromise. Instead of fully protecting the return vehicle, they reduce safeguards and trust that Mars will be less destructive than worst-case models predict. But the physics of the Martian environment offers very little reason for that optimism. And once we examine what happens to the spacecraft fuel itself during the long wait on Mars, when the situation becomes even more alarming, you think the rocket equation is unforgiving. The laws of thermodynamics are far worse. The farther humanity pushes toward Mars, the more we discover that space is not simply empty. It is hostile in ways that attack the very foundation of engineering itself. And nowhere does that hostility become more dangerous than inside the fuel tanks of a spacecraft waiting to return home. Most people imagine rocket fuel as something stable, a liquid stored safely inside massive tanks until the moment engines ignite. But the fuels powerful enough to lift human beings off another planet are not ordinary substances. They exist at temperatures so extreme that keeping them usable for long periods becomes a battle against physics itself. Modern high-performance rocket engines depend heavily on cryogenic propellants. Liquid oxygen must remain at temperatures near minus 183 degrees Celsius. Liquid methane, another leading candidate for Mars missions, must stay around minus 161 degrees Celsius. These are not ideal conditions chosen by engineers for convenience. They are absolute physical requirements. The moment these liquids warm beyond their boiling points, they begin transforming into gas and escaping from storage tanks. This process is known as boil-off, and it may represent one of the greatest hidden threats to a Mars return mission. The laws behind it are simple and merciless. Heat naturally flows from warmer environments into colder ones. The surface of Mars, even during its freezing nights, is still dramatically warmer than the temperatures needed to preserve cryogenic fuel. No insulation system is perfect. No storage tank can completely isolate itself from the surrounding environment forever. Slowly but continuously, thermal energy leaks inward. Molecule by molecule, the fuel begins disappearing. At first, the losses seem insignificant. A tiny percentage evaporates each day. But Mars missions are not short. Because of the orbital alignment between Earth and Mars, astronauts would likely remain on the Martian surface for well over a year before the planets align properly for a return journey. During those long months, the fuel required to leave Mars is slowly fighting a losing thermodynamic war. And thermodynamics never negotiates. A boil-off rate that appears harmless over a single week becomes catastrophic across 500 days. Day after day, the spacecraft quietly loses the very propellant needed for escape. Eventually, the terrifying possibility emerges that the return vehicle could reach departure day without enough fuel left to achieve orbit at all. The astronauts would not run out of fuel suddenly, and they would watch it vanish gradually into the thin Martian atmosphere long before launch. Engineers have proposed active refrigeration systems to slow this process. In theory, these systems continuously cool the fuel tanks to maintain cryogenic temperatures. But solving one problem creates several more. Refrigeration systems require uninterrupted electrical power for months. They contain moving mechanical parts that themselves degrade over time. They add mass to the spacecraft, which the rocket equation immediately punishes. They increase complexity, and complexity is exactly what isolated missions cannot afford, because every additional system becomes another possible failure point on a planet where no repair crews exist, no replacement hardware arrives, and no emergency rescue is possible. And yet, even the terrifying challenge of evaporating fuel may not be the most destructive force waiting on Mars, because the Martian surface itself contains something far more aggressive than scientists once imagined, something that does not merely sit on machinery, but actively invades it. In the next part, we confront the silent enemy coating the entire planet, a form of dust so corrosive and invasive that it may slowly destroy a spacecraft from the inside out. If the fuel problem on Mars sounds terrifying, then the Martian surface itself may be even worse, because Mars is not covered in ordinary dust. It is covered in one of the most destructive environments delicate machinery could possibly face. And unlike the dramatic dangers people usually imagine in space, this threat works slowly, silently, and relentlessly. At first glance, Martian soil looks harmless, dry red dirt stretching endlessly across an empty landscape. But under a microscope, the reality changes completely. The dust coating Mars contains chemical compounds known as perchlorates, highly reactive oxidizing agents capable of aggressively damaging both organic material and metal surfaces. These chemicals are corrosive enough to interfere with human biology, but for spacecraft systems, they create an entirely different nightmare. The danger becomes even worse because Martian dust is physically different from dust on Earth. On our planet, wind and water gradually smooth dust particles over time, rounding their edges through erosion. Mars does not have that luxury. Its dust remains jagged, sharp, and abrasive at microscopic scales. Every tiny particle behaves like shattered glass grinding against machinery, and because the Martian atmosphere is extremely thin, while the surface is constantly bombarded by solar radiation, The dust also carries electrostatic charges that cause it to cling aggressively to nearly every surface it touches. This means Martian dust does not simply settle onto a spacecraft. It invades it. It pushes into seals, valve systems, fuel injectors, moving joints, electrical interfaces, optosensors, and mechanical latches. Once inside, it combines with extreme temperature swings and corrosive chemistry to slowly dismantle the precision required for rocket engines to function safely. And rockets demand unbelievable precision. Inside an ascent vehicle, fuel injectors are engineered to microscopic tolerances. Tiny variations in fuel flow can destabilize combustion instantly. Rubber seals must expand and contract perfectly under extreme pressure without cracking. Mechanical release systems must trigger flawlessly during launch. There is almost no room for error. A small defect inside an ordinary machine might cause inconvenience. Inside a rocket engine, it can create catastrophic destruction in seconds. Now imagine those systems sitting exposed on Mars for over a year. Every day, temperatures rise and fall dramatically. Materials repeatedly expand and contract under thermal stress. Dust slowly accumulates inside mechanical interfaces. Perchlorate chemicals interact with seals and lubricants. Tiny fractures begin forming at microscopic levels. Lubrication thickens or breaks apart. Critical components slowly drift outside operational tolerances, and the terrifying part is that none of these failures announce themselves clearly in advance. A damaged seal does not flash a warning light. A partially blocked fuel injector does not politely inform astronauts that combustion stability is compromised. A dust-contaminated release latch may appear perfectly normal until the exact moment it is commanded to activate under full launch stress. That means the first sign of failure may happen during ignition itself. At that point, the astronauts are already strapped inside. Engines are firing. The pressures inside the combustion chamber are reaching explosive extremes. There is no ground crew standing nearby, no emergency repair team, no safe evacuation route. If a critical system fails during launch, the result is not a simple shutdown. It is violent structural destruction. And this is where the reality of Mars exploration becomes deeply uncomfortable. True, because the universe does not care about human optimism. Physics does not reward courage. Entropy does not pause for ambition. In the next part, we confront the harsh truth engineers rarely say openly, that surviving Mars may depend not on giant rockets or advanced AI, but on solving tiny mechanical problems humanity still does not fully understand. At the center of every Mars mission lies a terrifying truth most people never think about. Returning home depends on countless tiny components functioning perfectly after surviving one of the harshest environments in the solar system completely alone. Not mostly functional, not 99% reliable, perfect, because in rocket propulsion the line between success and catastrophe is unbelievably thin. A launch vehicle can appear operational right up until the exact second it destroys itself, a microscopic crack inside a seal, a barely visible obstruction inside a fuel injector, a mechanical latch slowed by dust contamination. Any one of these problems can instantly turn a controlled ascent into an explosion powerful enough to kill everyone aboard before the spacecraft ever leaves the surface. And that is what makes Mars fundamentally different from missions in Earth orbit. On the International Space Station, damaged systems can often be repaired. Replacement equipment can arrive from Earth. Engineers constantly monitor hardware performance from the ground, but on Mars, astronauts would exist inside a completely isolated environment separated from Earth by hundreds of millions of kilometers. Communication delays can stretch close to 20 minutes one way. Real-time support becomes impossible. Every system must survive alone. That isolation changes everything. Because the greatest danger is not one dramatic failure, it is the accumulation of tiny invisible degradations over time. A seal weakens slightly each day from thermal stress. Dust slowly grinds against moving surfaces. Corrosive chemicals interact with sensitive materials. Mechanical tolerances drift farther from their ideal ranges. None of these changes seem catastrophic individually, but together they create an environment where reliability slowly erodes until the spacecraft itself becomes unpredictable. And unpredictability is deadly in rocketry. The most frightening part is that many of these problems remain hidden until the exact moment maximum performance is required. During launch, engines ignite under extraordinary pressures and temperatures. Fuel and oxidizer must mix with extreme precision. Turbopumps spin at enormous speeds. Structural loads ripple through the vehicle instantly. Under these conditions, even a small imperfection can cascade into total system failure within seconds. A clogged injector may destabilize combustion. An aging seal may rupture under pressure. A jammed valve may interrupt fuel flow at precisely the wrong moment. Once ignition begins, there is almost no time to react. The spacecraft either works flawlessly or the physics turns violent, and physics has no mercy for wishful thinking. This is why many engineers and physicists quietly argue that humanity still lacks several critical technologies required for a truly safe Mars return mission. Not because rockets are impossible, not because Mars itself is unreachable, because maintaining long-term mechanical precision in such an extreme environment remains an unsolved challenge. We still do not fully know how to protect sensitive systems from years of perchlorate contamination. We still struggle to prevent cryogenic fuel loss over extremely long durations without constant maintenance. We still lack materials capable of enduring endless thermal cycling while maintaining microscopic structural integrity under abrasive conditions. These are not emotional barriers, they are physical ones. And physical laws cannot be negotiated with through confidence, money, or ambition alone. The universe only responds to working solutions, nothing else. Which leads to the final and perhaps most uncomfortable realization of all. The true obstacle separating humanity from a safe return from Mars may not be the enormous distance between planets. It may be something far smaller and far more fragile. In the final part, we confront the quiet mechanical weakness that could decide whether humanity's first Martian explorers ever come home at all. In the end, the greatest obstacle standing between humanity and Mars may not be distance, radiation, or even the enormous cost of interplanetary travel. It may be something so small that most people would never notice it. A microscopic crack inside a rubber seal. A few grains of electrically charged dust buried deep inside a fuel system. A tiny layer of corrosion spreading invisibly across a mechanical interface over hundreds of silent Martian days. That is the uncomfortable truth hidden beneath the dream of Mars colonization. Human civilization often imagines exploration as a battle against vastness. We picture giant rockets, massive launch towers, and planets separated by impossible distances. But physics repeatedly reminds us that complex systems rarely fail because of the biggest components. They fail because small weaknesses quietly multiply until the entire structure can no longer survive the stress placed upon it. And Mars may become the ultimate example of that reality. Everything required for a successful return mission must operate flawlessly after spending more than a year trapped inside one of the harshest environments humanity has ever attempted to conquer. The fuel must remain stable despite constant thermodynamic pressure. Mechanical systems must preserve microscopic precision through endless thermal cycling. Protective materials must resist chemical corrosion and abrasive electrostatic dust without continuous maintenance or repair. Every one of these challenges must be solved simultaneously. Not partially solved, not improved slightly, solved completely, because rockets are unforgiving machines. A launch vehicle that is 98% functional can still become a catastrophic failure the moment ignition begins. Inside the combustion chamber, pressures rise to levels where even tiny imperfections become deadly. The engine either maintains structural stability or it tears itself apart. There is almost no middle ground, and this is where the conversation about Mars often drifts away from scientific reality into emotional aspiration. Enthusiasm alone cannot overcome thermodynamics. Courage cannot negotiate with entropy. Inspiration does not stop cryogenic fuel from boiling away or prevent perchlorate dust from invading sensitive hardware. The universe operates according to physical law, not human optimism. That does not mean Mars is forever unreachable. What it means is that humanity is still early in the process. We are attempting to solve engineering problems that push material science, thermodynamics, chemistry, and mechanical reliability to their absolute limits. The challenge is not merely building a spacecraft capable of reaching Mars once. The challenge is creating a machine capable of surviving isolation, degradation, and entropy long enough to bring human beings safely back home. And until those problems are truly solved, monitoring the dream of standing on Mars carries a hidden risk far more serious than most public conversations acknowledge. Because the terrifying reality is this: getting astronauts to Mars may eventually become routine. Getting them back alive is the part physics still refuses to guarantee. Perhaps one day humanity will develop materials strong enough, systems reliable enough, and technologies advanced enough to defeat these obstacles. Perhaps future generations will look back at this era as the primitive beginning of interplanetary civilization. But if we genuinely intend to become a species that walks on distant worlds and survives there, we must first confront the laws of nature with complete honesty. The universe is not impossible to explore, but it demands precision, patience, and humility from every civilization that tries. If you enjoyed this deep exploration into the hidden physics of Mars mission, subscribe to the channel, leave your thoughts in the comments, and stay with us for more journeys into the science shaping humanity's future among the stars.